Hello, everyone. I'm Luboš Parobek, VP of Product and Go-to-Market here at Pachyderm. Today, we're going to be talking about DataOps and how to master it for machine learning. We're going to really cover three topics today. First, I'm going to jump into the journey that most teams take as they move from exploratory efforts in machine learning to being able to regularly and reliably deliver new machine learning applications to their customers. Secondly, we're going to jump into how DataOps fits into this machine learning journey and the specific challenges and opportunities that it presents. And lastly, I'm going to provide an overview of Pachyderm and how our data versioning, pipelines, and Lineage help teams tackle these opportunities and challenges. So almost every organization goes through a common maturity journey as they move from some exploratory analysis in trying to figure out how machine learning can really help their business, to getting their first models into a production application, and then finally expanding that success along multiple teams, use cases, and lines of business. Now, the initial phase is typically slow, manual, and error-prone. It typically involves a small team scrambling to gather data from a variety of sources, developing locally in notebooks, and typically involves very little automation. And the goal of this exploratory phase is simply to establish initial proof of concept and separate the hype from the reality when it comes to the value of machine learning for their business. And while a lot of teams spend time in this initial phase, it's really after this step that the real challenges begin. Actually getting that exploratory work into production efficiently and reliably, and proving that you can generate real business value entails a whole different set of challenges. You need to build out and utilize usually a complex set of MLOps tools to automate and productionize the machine learning lifecycle, and we'll jump into that in a couple slides. But by being able to automate and productionize that machine learning lifecycle, you begin to be able to speed up the deployment of ML models. It lets you scale out across multiple models, and importantly, it enables much better team collaboration. The final step is once one or two teams have successfully productionized the ML development workflow for their use cases and are generating real value. Of course, other teams want to jump on the bandwagon and figure out how to leverage machine learning as well. Now, without some centralized guidance, every team might try to adopt a completely different set of tools, different processes. So to avoid reinventing the wheel every time, you'll want to standardize and scale your MLOps tool chain and processes across all the teams in your organization. You're going to want to make sure that this toolkit enables and makes it easy for teams to train, to deploy, to retrain, to redeploy models frequently and with confidence. You're going to want teams to be able to collaborate and share and build on each other's work to be able to deliver results in an autonomous way, but in a way that is coordinated and allows them to leverage each other's work. Throughout these iterations and this journey, everything boils down to two key components, which you'll see throughout the presentation here, which is managing your ML code and also managing your data. So let's dig into that ML lifecycle. So the ML lifecycle is the workflow for how we get machine learning applications from idea to production. And it centers around this idea of managing both data and code. And of course, there can be some variance depending on your particular use case, but it usually boils down to the same four major steps. First is the preparation of data for experiments and training. Next, it's experiments and exploration to determine the data sets and the algorithms required for the models you're attacking. Third is the actual training and evaluation of models to determine which are successful for your application. And lastly, it's taking those models, deploying them in production and monitoring them. Now, importantly, these aren't linear steps. Rather, they're iterative and can loop around each other. So for example, in the experimentation phase, you may realize you don't have enough data or the right data, and you go back to preparation, for instance. And it's important that as you're thinking about your MLOps toolchain, that it supports this idea of iteration and automation as you work your way through this loop. So the first step in this process is data preparation, and it's a major focus for data ops in machine learning. And it encompasses activities such as data collection, often from a wide variety of sources, the transformation of data, the labeling of data, and finally, validation to ensure that the data meets expectations and is in fact ready to be used in the rest of the machine learning lifecycle. But it's important to note that data management activities, for example, versioning, tracking, and processing data continue throughout the machine learning lifecycle in phases like experimentation, training, and deployment. In fact, data ops has a large role to play here in terms of tracking things like intermediate results, data sets, metadata, and evaluation metrics. And this helps ensure that you always have that end-to-end reproducibility of results. This also helps immensely with data debugging and, of course, audit and compliance requirements. Let's look at some of the unique challenges that data ops can face when supporting machine learning. First, ML typically relies on very large data sets that often come from a variety of sources. And these data sets tend to also change frequently due to new or changed data. Let's take one example of using natural language processing for sentiment analysis. Large amounts of data might be coming in constantly from support emails, surveys, social media, and even voice transcriptions. And scaling and automating to handle this large amount of data can be challenging. Secondly, often multiple teams will be looking to leverage the same data set for different ML applications. For example, while this one team might be looking to do sentiment analysis on support communications, another team might be looking to use the same data set for a chatbot. To make things even more complex, often multiple data scientists on the same team may want to access these same data sets independently to explore new and different ideas and optimizations. Lastly, some of the most exciting and valuable ML applications like natural language processing use unstructured data. And unstructured data is basically data that does not fit nicely into database tables, but rather typically lives in files. So examples include unstructured text and documents, PDFs, for example, images, audio and video files. Some of the common challenges of unstructured data is that they come in a large variety of sizes, a large variety of file types, and this can often create challenges in terms of the processing of that incoming data. Lastly, supervised learning is one of the most popular approaches to ML with unstructured data, and it requires the labeling of data. Labeling can be particularly challenging in that it can be manual, expensive, and very time-consuming. Of course, data ops teams don't have unlimited budgets or time to deal with these challenges. They need to handle these new challenges in a cost-effective and timely manner that meets the needs of the data science teams they're supporting. To keep costs under control, they often need to apply new automation and scaling strategies. For example, being able to horizontally scale out processing while avoiding the reprocessing of data when possible. Data ops teams also need to make sure that they're facilitating collaboration. They need to enable a variety of teams and individuals on those teams to be able to share data sets effectively. This typically entails a robust data versioning strategy that allows data sets to be shared via concepts such as branching that enable a single source of truth to be maintained. A successful data ops approach and strategy will unlock several opportunities to accelerate machine learning in your organization. For example, it will allow data science teams to iterate on data faster. Preparing data can be a very time-consuming process that can quickly become a bottleneck for the rest of your ML lifecycle. Making sure that data science teams have the data they need when they need it is a key opportunity to increase the effectiveness and maturity of your machine learning lifecycle. Another opportunity relates to reducing the manual effort and errors associated with manually triggering data flows or manually tracking data changes. Automating these tasks is a key opportunity to save time and improve reliability. A successful data ops approach can also ease data debugging and data governance by providing a reliable and comprehensive version control system on data sets. This is key to not only improving productivity, but also meeting regulatory requirements. Lastly, as we discussed, some of the most innovative ML use cases are being built upon unstructured data like images, video, and text documents. Let's look at a few examples. NLP is one of the most popular and includes things like sentiment analysis, voice-to-text transcriptions, or analysis of financial and legal documents. Computer vision is another one that includes things like medical diagnoses of x-rays or CAT scans, and facial and voice recognition for authentication. Geospatial analysis examples include being able to analyze satellite imagery for crop yield forecasting or recognizing logistic bottlenecks. A data ops approach that makes unstructured data a first-class citizen will allow your data science teams to more easily pursue these high-value use cases. This means making sure that your data ops approach can handle ingress and processing of very large numbers of files, as well as being able to handle individual files that are very large in size. Some examples include, it's not unusual, for example, for high-resolution satellite images to be hundreds of gigabytes in size. Lastly, your data ops approach should be able to handle any file type, because as we've seen, they can come in a variety of types. Okay, let's switch gears and take a look at what a typical data ops pipeline looks like. Most commonly, it's going to be composed of three parts: ingest, transformation, and validation. Ingest is the first step and enables raw data to be brought into the system from a variety of sources. They might include databases, CSV files, object storage, and then we want to go ahead and combine them. Ingest typically supports both batch processing as well as real-time streaming. To prepare ingested data for experimentation and training, it needs to go through varying degrees of transformation. Examples include standardizing file names, converting image files into a standard format, or removing extraneous columns from a CSV file. The last step is data validation, which seeks to ensure the quality, usefulness, and accuracy of the data. Validation increases confidence that the data being consumed is clean and ready for use by ensuring it meets minimum expectations. A good example of validation includes detecting missing data or outliers in your data. Next, let's look at some of the key requirements for data ops pipelines to support machine learning in particular. In terms of ingestion, we've already mentioned the need to be able to combine several data sets into one, as well as being able to support both batch processing and streaming. In addition, ingestion should support unstructured data sources like object storage, as well as any file type. For example, image, video, and audio files. Ingestion should also be able to efficiently handle large volumes of data that are changing frequently. For example, Internet of Things sensor data or satellite imagery. In terms of transformation and validation, it's important to be able to scale processing quickly and efficiently. Through approaches like horizontal scaling and parallel processing, it's possible to take an ML job that would take days to process sequentially and reduce it to hours. This ability to quickly and efficiently process large data sets is key to enabling those quick iterations that you want for your ML teams in experimentation and training. You don't want data preparation to become a bottleneck in your ML lifecycle and have teams waiting days in order to complete new experiments. It's also important to build in flexibility in terms of the languages and tools your pipelines will support for transformation. You'll often see different teams will want to use a large variety of ML tools, and it's important to enable these teams to have the freedom to use the best tool for their particular machine learning task. Collaboration is also an important aspect to consider. You'll want DataOps pipelines that make it easy for teams to work autonomously against common data sets, but without disturbing each other's work. And also without necessarily duplicating storage or processing of shared data sets, again, because we're dealing with such large data. Lastly, because data plays such an important role in the effectiveness of machine learning, you're going to want an effective way to debug data issues. So for example, if you have a new training data set, if a new training data set results in a model that's performing poorly, you'll want to be able to quickly understand the root cause from a data perspective. Basically be able to unwind that and step back in time. Also, if you're in a regulated industry like life sciences or financial services, you'll want to make sure that your data pipelines support your required data governance and audit obligations. Let's switch gears now and talk about how Pachyderm can help you build DataOps pipelines that will help accelerate your machine learning journey. So Pachyderm provides two key capabilities that you're going to want in any DataOps stack. These are data-driven pipelines and automated data versioning and lineage. Let's take a look at how our pipelines working in concert with our versioning can help you meet many of the requirements we just discussed. First, Pachyderm pipelines allow you to automate your data preparation tasks into flexible pipelines. These pipelines are completely code and framework agnostic, so you can use the best tools for your particular ML applications. Our capabilities are also highly scalable and are particularly optimized for large amounts of unstructured data. Everything in Pachyderm is just files. So we work with any type of data, images, audio, CSV, JSON data, you name it. And we can automatically parallelize your code to scale to billions of files. Because Pachyderm understands versions and diffs of your data sets, we can offer some incredibly unique capabilities, such as incremental processing, where we only process diffs or changes to your data, and this can reduce processing time by an order of magnitude or more. Lastly, we keep track of all changes to your data. This includes metadata, artifacts, and metrics. So you have end-to-end reproducibility, which provides immutable data lineage. This significantly reduces the effort to debug issues and help satisfy data governance and audit requirements. Pachyderm Enterprise is our commercial product offering. It's container native, and we run on any Kubernetes flavor in any of the cloud-managed Kubernetes services or on-prem. This lets Pachyderm leverage the cloud provider's core compute, storage, and network resources. And because we're cloud and infrastructure agnostic, you can easily switch between clouds or have a hybrid or private cloud system. This gives you full portability for your entire DataOps system. And all of these infrastructure concerns are abstracted away from your core ML engineers and data scientists who just want to focus on iterating on their models and getting things out to production as quickly and as reliably as possible. Let's double click into a bit more detail about Pachyderm's key features of versioning, pipelines, and lineage. Pachyderm's unique data versioning capabilities ensure that you have a complete auditable record of everything with minimal overhead. First, all data is versioned automatically in data repositories using a Git-like approach that supports concepts such as commits and branches. This enables effective collaboration on shared data sets by multiple individuals on a team while enabling them not to disturb each other's work. It also makes it easy to identify and revert bad data changes in near real time. Secondly, Pachyderm supports petabytes of data while minimizing storage costs. We do this via a very unique storage architecture that utilizes content-based deduplication to dramatically reduce storage requirements. Next, our file-based versioning provides first-class unstructured data support by being able to handle files of any type or size. Pachyderm also provides a complete audit trail for data across the entire ML lifecycle. In other words, Pachyderm doesn't just track changes during data preparation, but into experimentation, training as well, giving visibility into all model artifacts and intermediate results. Lastly, our versions are stored as native objects, not metadata pointers. This means that data objects that are committed are not just metadata references to where the data is, but actual version objects or files. And this means that it's impossible for that lineage to ever be lost. Next, let's take a look at our pipelines. Pachyderm pipelines transform ad hoc processes into integrated and reliable workflows. Pachyderm pipelines are responsible for reading data from a specified source or input repository, executing code, and then writing the result to an output data repo. Pachyderm pipelines are language and framework agnostic. Our Kubernetes native approach means that Pachyderm can run any code that can be put into a container. This lets data scientists and ML engineers choose whatever library works best for each pipeline step and makes transformation and validation of raw data much easier. Secondly, Pachyderm can auto-scale data processing without any additional code being written. Pachyderm pipelines can be configured to automatically parallelize based on the data and file structure in your repos. This significantly reduces processing time without you having to know sophisticated parallel programming approaches. Next, Pachyderm's pipelines are automated and fire whenever new data is detected, saving developer time and avoiding mistakes. Pachyderm's pipeline engine is constantly watching for changes in input data repositories. Each time new data is detected, Pachyderm deploys a Docker container containing your code to process that new piece of data. Lastly, because Pachyderm's pipelines are working hand in hand with Pachyderm's versioning, the pipelines are smart enough to know when new or changed data has been committed versus duplicate data. Pachyderm can be configured to only process new or changed data, significantly improving processing time and saving processing costs. Working together, Pachyderm's data versioning and pipelines allow you to have immutable data lineage. This means that with Pachyderm, you're able to track every version of data and code that produce the result and maintain compliance and reproducibility. You're also able to manage historical relationships and data states and provide a complete account of every step in the journey of your data. Lastly, our global IDs make it easy for teams to track any result all the way back to its raw input, including all analyses, parameters, code, and intermediate results. And it's important to emphasize that Pachyderm's data lineage is immutable, enforced, and automatic. Many solutions track lineage by just logging some metadata to a database, oftentimes done in the user code itself. But this requires everyone to use the system perfectly every time. And just like a chain of custody for evidence, even if 95% of the time it's done correctly, one break in the chain can completely ruin your reproducibility. Pachyderm's data lineage is fully enforced by the system for every step in the process. You literally can't run a Pachyderm process without lineage being recorded. And it's all tracked as a fundamental property of the data, completely behind the scenes, without ML teams having to do anything on their own. Let's take a look at a few examples, a few companies that have seen huge improvements in their machine learning operations by implementing Pachyderm. LogMeIn is a great example of a company that saw huge processing efficiencies through Pachyderm's scaling benefits. They decreased their processing time from 7 days to just 7 hours. Royal Bank of Canada is an excellent example of a highly regulated organization that is able to continue to innovate quickly while meeting their strict compliance requirements using Pachyderm's Lineage features. And lastly, LivePerson is a good example of a tech company that's able to handle complex data processing and model training needs through Pachyderm's automation features. They also reaped substantial benefits in terms of speeding up their team's agility by decreasing processing time from 10 hours to just 1 hour. I hope that today's session on data ops for ML was informative and it took you a step forward in your ML ops journey. If I've piqued your interest in Pachyderm, you can learn more by visiting us at pachyderm.com, where you can find more product information, case studies, and sign up for a free trial. I think next we're going to move to questions, but thanks for your time.